A fundamental relationship exists between the electron and hole concentrations at thermal equilibrium and is given as NO into PO equals to Ni square. Now what is NO? NO is nothing but the thermal equilibrium concentration of free electrons. And what is PO? Thermal equilibrium concentration of free holes, right? And what does Ni stands for? It is nothing but the intrinsic carrier concentration. What does it mean? Intrinsic carrier concentration is nothing but the concentration of free electrons and holes. Total concentration of free electrons and holes is nothing but eta I, right? Now at room temperature, say at temperature T equals to 300 Kelvin, each donor atom, what it will do? It will donate the free electrons to the semiconductor. Now at this temperature, if the donor concentration Nd is much larger than the intrinsic concentration, that means the donor number is more as compared to the total concentration of free electrons and holes, then in this case your total PO, what is PO? The concentration of free electrons at thermal equilibrium can be written as eta I square upon Nd, where Nd is nothing but the concentration of the free electrons at the equilibrium. Now we can say the intrinsic semiconductor concentration is less than the number of the donor concentration at the temperature 300 Kelvin. Similarly, we can write for the other part. That means at temperature T is equal to 300 Kelvin. Again, we can have the acceptor concentration. Now, Na is very much greater than the intrinsic semiconductor concentration. Now, what you can see from this, your PO is approximately equal to Na. So, I can write NO as the number of concentration for the free electrons can be written as Ni square upon Na. The concentration of free holes is replaced by the total number of acceptor concentration in the structure. So these 2 points conclude the intrinsic and extrinsic semiconductor types.